Okay, so what I want to do today is a couple of example problems. So I'm going to begin with example 7 point, actually problem, chapter 7, question 45. So you have, we make life easier. We have a superconducting infinite plane. Okay? So presumably this part of the universe is filled with the superconducting material. And then you place, and for us, what does that mean? It means the magnetic field inside is zero. It also means the normal component of the magnetic field is zero, because the normal component of the magnetic field is continuous because divergence of B is zero. The tangential component is not zero because this will create a surface current. And we'll work all of it out. Okay? So let me do that. So here is a distance h above the superconductor. You have a magnetic dipole. Let's call it M1. It's really M, but as I mentioned, it might induce a virtual dipole, and we want to call that M2. So B normal above minus B normal below is zero because divergence of B is zero, and inside a superconductor, this is zero. Therefore, this also has to be zero. And then B parallel, it's a vector, meaning the xy component of B above. And please look this up. I want to make sure I'm writing this correctly. B parallel below is equal to the surface current cross N. And N, I just go somewhere far away. This is going to be my N, the unit normal. Let me make sure I have the sign correct. Yep, it is correct. Good. So what's going to happen, as we'll see, is we want this condition to be satisfied. If this condition is satisfied, and of course, this is zero. To satisfy, and that's all we need. We need to make sure B normal is zero. And when you do that, you will find that B parallel exists. And if B parallel exists, K exists. So this will start inducing a surface current. It's going to spin around like this. Yeah? It's going to decay far away from this dipole because it's reacting to this dipole. As a result, it creates an effective magnetic dipole. And you will see that, so since we know the story ahead of time, what we're going to do, we're going to go the same distance. So this is h, and the same height below, in anticipation, and we're going to consider this problem. And we will show that this configuration, so this, mind you, this is a virtual. It is there strictly for boundary condition to be satisfied. There's no dipole someone has dug up and is inserted over there. So that's the same h below. And because of this virtual dipole, all sorts of interesting results appear, and it looks super interesting to us because it's a virtual dipole and it has real effects. Okay. Now recall the expression for the magnetic field for a pure dipole. it is, and I don't want to waste your time, or even worse, have inaccuracies. It's mu0 over 4 pi 1 over r cubed. It is r cubed. It's dipole. It's not monopole. And we've seen this before. M dot r hat minus m. This is B due to M. Okay? So that is just recall. So we're going to use this to literally add up. That's for just a pure dipole. We're going to use this formula to add up the two dipoles. It's as simple as that, just keeping algebra straight. We have intuitively solved the problem. And the diagram here is, if this is M, whether it's plus or minus, and you're computing the field somewhere over here, R, let me clarify, be evaluated at the point R. So this R hat means the unit vector from where the dipole is located. Yeah? So anywhere in this region, the magnetic field, if this is true, we're assuming that this virtual dipole kind of works out. If it is true, would be nothing more than the sum of two dipoles. Let's pick an arbitrary point, well, let me first do this. Well, I don't care about B everywhere. It is B due to the two dipole. So B above. B above is the B due to the two dipoles. But I'm more concerned with showing this boundary condition. So I'm going to calculate B at the interface. So I'm going to pick a point here. And I'm going to let me label a few things. This is M2. So this unit vector, I'm going to call it R2. This is actually R, is script R, if there is if the dipole is not located at the center. That's fine. And this one, I'm going to call it R1. I need to label angles, so I'm going and distances. I'm going to call this cylindrical S, because in the XY plane we can use a nice cylindrical coordinate system. This angle is chi, so this is also chi, and which means this angle is chi. That's too many labelings. It's a bit tight, but there it is. Can you all see? Because these are two parallel lines. This is a transversal cutting it, so this angle is the same as that. This angle is the same as that. Okay? So then B at the interface. Is, of course, mu0 over 4 pi. The only place of distance, the distance from here to here, it's h squared plus s squared, Pythagorean theorem, square root of that. So, and then we need to cube it. So it is s squared plus h squared to the 3/2. And let me now write the three vectors. This is not very spectacular. Just you can see what I'm doing. It really doesn't require any explanation. Minus m1 plus 3 M2 R2 R2 M2. One of the advantages we're going to have is these two terms are going to cancel off because M1 is M1. So vectorially, right? So those two terms are going to cancel off. We just need to simplify this. So let me bring all the terms possible. I have mu0. In anticipation of more space, I may not need it. Mu0 over,
in our original formula, we have hats for our script R's, and then here we have their vector notation.
Yeah, it's unit vector. These guys are unit vectors.
And the outside, no, both, okay.
Yeah. Thank you. It's good to be consistent. So let me compute this. I get, I put a vector on 3. Did you
Yeah.
Why not? Put a vector on the parentheses. I have not intentionally, once when I was signing my name, on top of the G, I put a vector symbol. You know, it was right after class. So there's this 3, the magnitude of this guy, M. Now I need z hat dot R1. Z hat dot R1. Cosine of the angle between them, it's pi minus chi. So cosine of pi minus chi, and then R1 hat. These two cancel off, I'm not even writing them. 3m cosine. Again, this is minus z2. That is this one, R2. I think great, this is also pi minus chi. Because this is chi, this is pi minus chi. So they actually they just double, except for this. Well, they don't double, they just factor out. Pi minus chi R2. And you'll immediately see the advantage here. So then I have mu0 over 4 pi 3m cosine pi minus chi over s squared plus h squared to the 3/2 R1 plus R2. Yeah? And guess which way R1 plus R2 points. These are equal and opposite in length. It is tangential. So the cure to the normal component being 0. This is purely tangential as boundary conditions require. So let's very quickly write the current, the induced current. That's easy to do. I may need this shortly. So mu 0 over 4 pi 3m pi minus cosine. I think we can simplify cosine of pi minus chi. Oh, let me also, sorry about that. Let me do this. R1 plus R2. We know it's going to be in the S hat direction, right? So we know the direction is going to be S hat. These, both of them have the same magnitude. So it's 2 times the magnitude of R1 and R2 times cosine of the angle between them. So 2 times cosine chi, yeah. Nope. Why do I have sine chi? It is sine chi. Yeah, what's the, let me make sure. So, what am I trying to do? I know it is something S hat. Let's find the square of this. So, R1 plus R2 squared, which means dotted by itself. It's R1 squared, 1, plus R2 squared, 1, plus 2 times R1, R2, 1, times cosine of the angle between them. Cosine of what? Isn't it 2 chi?
Yeah.
Or are they 90 degrees? They're not 90 degrees, obviously not. So it is pi minus 2 chi. I have it as, maybe that's what it is. Pi minus 2 chi. Good. So that is 2 times 1 plus. What is cosine of A plus cosine of B? Cosine A minus B? It's cosine A cosine B plus sine A sine B, is that true? Or minus sine A sine B?
It's A minus B is in the parentheses.
Yeah.
Cosine A, cosine B, plus sine A, sine B.
Cosine A cosine B plus sine A sine B. What is cosine of pi? -1. Ew, this is not looking good at all. 1 minus cosine 2 chi. What is sine of pi? Oh, maybe it is looking good. What is 1 minus cosine 2 chi? We can use the double angle formula. We already have this, so we don't need this. There's a formula for cosine 2 theta. Cosine 2 theta is 1 minus sine squared theta over 2 or something like that?
Cosine 2x is
Yeah.
1 minus 2 sine squared x.
1 minus 2 sine squared x. No divided by 2, nothing?
Mm-hmm.
So then I would get R1 plus R2 squared equals 2 times 1 minus 1, right? Plus 2 times sine squared chi. Sine squared chi. Thank you. 4 sine squared chi. So then, because I know the answer, I have 2 sine chi. It works out. Okay? Good. So now, let's write the expression, final expression. B and the interface is equal to what? Mu 0 over 4 pi 1 over s squared plus h squared to the 3 halves. 4 pi 3 halves cosine chi times 2 sine chi s hat. And that should be equal to k cross n. N is a unit vector, so what must be k? What gives outside? What cross n gives outside?
S cross B gives Z, right?
Phi cross n is outside. Yeah? So the answer for k, so I did forget one thing. It is mu 0 and whatever the mu is over here. But that doesn't matter.
Because the other expression was for H, right? If there was no mu. I was looking at it earlier.
Correct. Yeah. So then k is equal to, but we can do one simplification. At the interface, h is fixed. So that's what it is. The mu 0 goes away, so I have 1 over 2 pi s squared plus h squared cosine chi sine chi phi hat. Kf cross n, I have a minus. Phi hat cross n is s hat. Yeah, did we have a minus in the b? Yeah, actually I do have a minus in the b. I don't know where the minus came from. Let me. Cosine pi minus x. Cosine pi minus x is minus cosine x. Yeah? Because it's cosine pi, cosine chi. We just use that. Plus sine pi, sine chi. Yeah? And cosine pi is -1. Yep, so that's it. Good. So the point is, for it to have a dipole pointing down, the currents have to be going this way, minus phi hat. Yeah, I wanted that feature for sure. That is almost what I have here. I can put the expression for chi, sine chi, and cosine chi. That is -1/2 pi, 1/s² plus h squared to the 3/2. If I look at this triangle, what is sine chi? It is s over this. S over s² plus h squared square root. And the other one is what? Cosine chi is h. That's -1/2 pi sh s² plus h² to the 5/2 phi hat. Yeah? I want to calculate, and then I want to give you the setup for the next problem, because it's very similar. The force, so the question is, why is this floating? So this must, it is repulsive. The question is, at what height will it float? If you know the mass of these guys. Okay, fine. Everyone good? Okay. What's the expression of force? So I want, let me write this. Force on M1 due to M2. Dipole force, so it's the gradient of M1 dot B, let me call it B2. B due to the virtual dipole. Okay, let's write an expression. M1 is easy. M1, I just wrote it. M1 z hat. B2 is equal to μ0 over 4 pi, watch this, 2h cubed. The distance is 2h. You don't have to worry about all the details, but I'll tell you why I'm cheating. Then I have 3 m1 z hat dot, r hat is nothing but z hat, another z hat minus m2, so that is plus m z hat. I guess I can call it m2, but then I'll replace m2s with m now. Yeah? So you agree, serious lack of space, I don't need this anymore. But I'm also slightly cheating. I'll tell you why. It's better to first pull the Jedi mind trick and show you that it works, and then show you where I'm maybe possibly cheating. So there is this B2 equals mu0 over 4 pi 1 over 2h cubed minus 2m z hat. Yeah? Because I did two things here. I got rid of this m2, and we'll call it m. It's the same magnitude. It just points differently. This is minus 3. This is 1. So it's minus 2. And so m1 dot b2, what is that going to be equal to? Minus mu0 over 2 pi m squared over 2h cubed. Yeah? H is nothing but the z coordinate. Two cubed is 8, 8 twos is 16. Z cubed. And then force. Why don't we factor out most of what we can? I was getting worried about this negative sign here, but thankfully the gradient of z cubed, 1 over z cubed, makes it positive. Good. The magnet floats. See, I'll tell you the cheat. I replaced 1 over r cubed by 2h cubed. That is true if the magnetic field is here. But to take the gradient, you have to take it in all directions. Yeah? But I didn't have to because it is m dot b. And m points only in the z direction. So the only thing that, will survive is the z axis. Otherwise, this is just not allowed. And so mu0 m squared is a 3 over 16 pi z to the 4th. And now I can make it h to the 4th, except I have 32 pi. 16 pi z to the 4th. If I recall when I calculated it, it was 32 pi. Everything else is good. In the z hat direction, where could I have missed? Eight twos are 16. So factor of 2, right? cubed, so 2h cubed. Doesn't that look legitimate? So then let's look at, so this is 2m. Yeah, I remember that. Oh, but what I meant to say, first of all, this is h cubed. I mean, h to the 4th. I would like for you to track that down and tell me where I could have made a mistake. Is it obvious we have u0, 4 pi, b2, Chip, any ideas?
Can't find anything. You think we do it over there, you might forgot to cancel that out or something?
No, no, that's a problem. That is the problem. If this didn't exist, we'd be okay. We would have 32. But I canceled it and I made it 2 pi. But we can't just cancel it. So,
It has to be a step earlier, right? This one.
yeah, but this directly just follows from the yeah, I think it could be. See, suppose I replace 2h with z. And then if I took the derivative, it would be minus 3
But it's not actually z.
over z to the 4th. So what I should really do, because the height between them is, if I call it z, it's actually 2h. And then at the end, replace z with 2h. So if I did that, so I don't know if that's the cure. I could be, so, 2h is what I'm replacing z with. And then I take the derivative. I get 2 pi z to the 4th. And then I get 2 pi. Yeah, maybe that's what it is. Please make sure that I'm not just seeking the answer I get. Then I replace z with 2h. So then I get 3 mu 0 m squared z hat over now 32 pi h to the 4th. Yeah? So then, yeah, I think that's what it is. Hasty derivative taking. But I want to make the point. In fact, if you want to know how high the magnet is going to float, it is really doing this. mu 0 m squared over 32 pi h to the 4th can now be written as mg, where this is the mass of the magnet. And if the question is what is h, you can say h to the 4th is 3 mu 0 over m squared over 32 pi mg. That's the height at which the at which the magnet will float. You understand what I did there? I replaced 2h with the variable z. What you want to call it, whatever variable you want, you call it. Yeah? And then I took the gradient with respect to z. Because the true distance, it's with that that's the distance with which we're taking the gradient. Okay, please check to make sure that I'm not just forcing an answer. I'll think about this as well. And then you can get this. Now, it turns out when you do this, this is not the height at which the magnet is going to float. This is not a very stable, it could. This is not a very stable equilibrium. If you just tap it gently, it's going to do this. So the very next problem says, well, don't fix the angle. And I want you to do this problem. Don't fix the angle. But now do this at some theta. So then what would you have to do? Well, you have to do the virtual image to be this. This will also be theta. This will take care of the boundary conditions. And then compute the magnetic field. You'll find that this also satisfies. So at any angle, it'll satisfy. But then compute the torque, not the force, the torque on this due to that. And the torque on this one due to this one. And you'll find that the torque vanishes here, here, and here. But the only stable one is going to be the horizontal. That means if you perturb it slightly, it's going to come this way, and it's going to do and settle over here. That's what it means. And I'll help you set it up if you have questions. So homework, make sure you try to argue that it has to be 32 and not 16.